This is lecture 6D for Calculus 2 on some more difficult examples of work problems. In more difficult work problems, the mass of at least part of the problem is specified as the density. So the first one we're going to do is that of hauling up a bucket and a rope. And we're going to let the force be specified in pounds, but we'll see we still have to do some integration here. So the question here on this example is, how much work does it take to haul up a 200-pound bucket of hot tar onto a 350-foot roof, and you're hauling it up with a cable or a rope that is 5 pounds per foot. These kind of problems are divided into two sections, but the first thing you do, the cardinal rule, the most important thing, the crucial thing, the thing I cannot stress too much, is make a sketch. If you cannot make a sketch, then you cannot solve the problem. And usually, once you make the sketch, the problem is already solved. Right? And I'm going to point out now, and then I'll point out later in this lecture what I do. Right? And you can feel free to use my conventions, although there are others. I always put the y-axis, sometimes the z-axis in a three-dimensional problem, as the height. This is your height above the ground. I do not use x, I use y. X is distance along the ground, y is height. Okay, and y equals 0 is ground level. Now there's other people who would put the 0 up here at the height of the building and then go down, and that's fine, and you're certainly welcome to do that if you can keep things straight. This is what I do, this is how I was trained, and it works. Okay. It's also better that whatever convention you adopt, you continue to use it. Otherwise, you're going to end up with sign problems. It's not the end of the world, you just end up with sign problems, and it's more complex. So this is what I'm doing here. Here's my sketch. The red, right here, this red part is the building. It's 350 feet high. Here is my 200-pound bucket, and here's my rope, the density specified, and then this is what I'm going to talk about in a few minutes. This is all you have to do for a sketch. It's not a work of art, but it's supposed to be a very practical sketch. And so I have the sketch made. And what I'm going to need to know, and that's why I've circled it here, is that I'll need to know the distance to the roof from every point along the rope. And the way I've set that up, the distance to the roof, to the top of the roof, is 350 feet minus y. For example, how far does the coal bucket have to go up to the top of the roof? The distance for the coal bucket, or rather the tar bucket, is 350 minus 0. It has to go 350 feet. How far does a section of rope that's right here, say at 300 feet, have to go? Well, the distance for that section of rope would be 350 minus 300, see, because that's the y location of the rope, 50 feet, which is obvious. It only has to be hauled up 50 feet, whereas the bucket has to be hauled up the whole 350 feet, and I need that specified, and I specify that here as d equals 350 minus y. Your function will not look like that if you do not put your 0 at the ground level. To solve these problems, you break them into two parts. For the bucket that you're trying to hoist, it is a constant 200 pounds. So this becomes the typical, let me get the pin here. This is our typical work problem, x1, x2, function, force varying with x, dx. In this case, that force is a constant 200 pounds, comes out from under the integral sign, you carry out the integration, and you get how much work it takes to haul the tar bucket by itself up. Now the second part of the problem is hauling up the rope. And this is done in the typical calculus manner. This is how you work up to this, and later on you'll be able to just write the integral. You take the rope and divide it into these little sections, right? And you compute the force in each section. The force here is the density of the rope. It's given in kilograms per meter. No, it was given in pounds per meter, sorry. So it's in pounds per foot, all right? That's the density of the rope. And you multiply it, this is British units, so all you have to multiply it by is how far it's going to take you to get it up to the top. So the force is going to be density times dy, and dy is just the height of this little section here. So when I multiply this by dy, I now have the force. Actually, since we're doing it discrete, we'd have rho times delta y. Okay, that's the force in the ith section. Okay, we're assuming delta y is the same for all the little sections, and rho is the same in every little section. There's your force. Right? Now, if you want the work in that ith section, would be the force in the ith section times the displacement. But what's the displacement? You have the force, it's how far it is up to the top. So that would be the height of the building, which in this case is 350 minus y. So y is the location of this little section. I compute the force in it. All right. Then I multiply that by the distance to the roof, the total displacement that that little piece of rope undergoes. Okay, I've made a big mess on here, and because this is so important, I'm going to erase all this and do it again. Right. I want to haul the rope up. The rope is specified by some density, and the density, that's a rho, Greek letter rho, is in this case it was 5. Oh, do I like to kilograms? Just a second. Pounds per foot. Right. This is density. I need force. I need just plain old pounds, not pounds per foot. So in each section, let's say this section right here, I calculate the force, which is going to be the density in the section times delta y. Delta y is the width of each one of these little sections. Then I need to calculate the work in each section. That would be the force times the displacement. Okay, displacement. And what is the displacement? It's the distance that it's going to go to the top of the roof, which is the height of the roof, 350, minus yi, or yi is the location of that little section. All right, I think you can see exactly where we're going to go here. We're going to add up all of those so we have a discrete sum. Then we're going to take the limit. So here's a summary, and by now you're probably tired of hearing it because you understand it. First thing, always make the sketch. To the sketch, add your coordinate system. That means specify y. All right? Specify what is height, where 0 is. You need that. And again, I say usually without fail, I put the origin on the ground and I use y, sometimes z, but never x for the up direction. Then partition the rope into little sections of height dy. I should have said delta y here. Let me fix that. Delta y, and calculate the force in each section. The force in the nth section is the density times delta y, if you're in British units. And I'm going to go ahead and move to MKS units. You would have force in the nth section is the density times the acceleration due to the gravity, delta y. Remember, here you would be given kilograms per meter. You would have to multiply by acceleration to get force. Then you have to figure out the distance from each section to the top of the roof. Right? Add that will give you your work when you multiply those two together. Add up all the works for each little section. That's a crude approximation. Refine the partition by dividing the rope into smaller and smaller sections. Finally, you take the limit, and then you get you're able to compute the work in the rope. Right. So what do I have here? I have an integral from y1 to y2 of the density, because it's in pounds, I don't have to multiply by acceleration, times that function that gave me the displacement to the top of the roof, dy. It's kind of different from what you're used to. You see the rho and the dy actually give you the force. Used to thinking that's the displacement, but it's not. Displacement's in here. And here's a summary. This is the take-home equations. For a rope problem or cable problem, if you're in British units, the starting, and let's just say you're going up to a building from ground level, this could be adjusted, obviously. You take the density of the rope, which is going to be in pounds per feet, you multiply it by this term here, which gives you the distance to the top of the roof, dy. Okay, if you're in MKS units, then you take that rope density, which will be kilograms per meter. Okay, you multiply it by the acceleration due to gravity. Now you have force. Then it's the same. You multiply it by the displacement, the term giving you the displacement, and you're integrating over y. H is the height of the building, or the height you're hauling it up to. Okay. What if you're hauling it out of a hole? If you're hauling it out of a hole, this might be like saying -50 if it's 50 meters down into a hole. Here's my example. There's the ground. I have a rope here, and let's say the height of the building is 300 feet or some, I don't know, platform, and you want to haul it all the way up to here. Now you're going to integrate. This is 0. This is -50. So now you'll be integrating from -50 to 300. Okay. Now we're going to do the second hard problem. And in this one, you're going to pump fluid out of a tank from the top to the top of the tank and then out. And you want to know the work it takes to pump this fluid that's all in here in this very bad sketch, but that's not the point. It's got the essential things on it. You got fluid in here and you want to pump it up. And that's the work that you want to know. Once it gets here, you just let it go. Or that's a different problem anyway. So here's the procedure. Now you divide the tank into slabs of height dy, or you could say delta y. So this is showing you right here the height of each little slab. Okay, right there. Now let me get the pin. The height of this slab right here is delta y or dy. Okay. Divide it up. Then you will be given the density. All right. The density of the fluid is given as kilograms per cubic meter. Or if you're in British units, it'll be pounds per cubic foot. So now, to get the total mass, right. So force, in this case, you need the force on this. So if you have pounds per cubic meter, which is how the density is reported for the fluid, you need to multiply by cubic meter to get plain old pounds, which is your force. Right? What is cubic meter? That's the volume. So we need the volume of this little section right in here. And the volume is going to be the cross-sectional area, that's the area here shown like this, times delta y. That will give me the height of this little section. So we need the area, the cross-sectional area of the tank. Right? In the square tank, it'd be length times width. If you had a circular tank, it'd be pi r squared. So that's the cross-sectional area of the floor of the tank, and then you multiply it by delta y, which is the height of each little slab that you've divided it into. Then the problem is quite similar to the other problem, because now you have to multiply it. Now you have work, or the force, and you have to multiply it times the distance to the top of the tank. And again, the distance is h minus y if you set the coordinate system up the way I did. So here's a summary. The first thing at the top of the summary, unfortunately, it's a little high, so you can't see it so well. Let me fix that. Okay, so the first rule is make a sketch and show your coordinate system. Then you partition the tank into little slabs of height dy or delta y. You need the distance from each little slab to the top of the tank. In my coordinate system, that's the height of the tank minus y. Y is where the slab's located. Calculate the cross-sectional area. Then you calculate the force in each slab this way. If you're working in British units, here's the force. It is fluid density times the volume. That means fluid density times area times dy. If you're in MKS units, you have to start with that fluid density, then you have to multiply it by acceleration due to gravity, and then you're back to the volume again, which is, again, area times dy. So here's an example. Say you have this, we're going to say temperature-controlled, Olympic-sized swimming pool located on Saturn. Right. And it's full of glucose. Maybe you need to feed astronauts or something. And the density of this glucose is 1,400 kilograms per cubic meter. Right. Here's the acceleration due to gravity on Saturn. We need that. So here is the tank divided up into these little slabs. Here is the distance. It's okay. Olympic-sized swimming pool. It's 50 by 25. So the cross-sectional area, because it's rectangle, is 50 times 25. The volume in each slab is that area times dy. Area is 50 times 25, and then here's your dy. Right. So the force in each slab, because we're in MK units, is that density times the acceleration due to gravity times the volume. The density was 1,400 kilograms per cubic meter. I have to multiply by the acceleration due to gravity on Saturn, which is 11. I need to multiply by the cross-sectional area, which is 50 times 25, and then times dy. So here's the expression for force. Now I need the distance to the top of the swimming pool. This is 3 meters. There's no, it's just straight 3 meters. So, okay, we don't have a complexity there. But you see, you could, if you had this, if you had one with a shallow and a diving end, it would be different. Right? So now what's the work going to be? The work is going to be this integral. y1 to y2. y1's at the bottom because that's where you're starting. It's going to be the force, all right, and the force over this integral, and it looks like this. I want to keep the parts straight. That density times the acceleration due to gravity times the cross-sectional area times the distance to the top over dy. And these are all the parts we're going to see here. So it would have been 1,400 times 11 times 50 times 25, which is that cross-sectional area. The distance to the top was 3 minus y dy. Of course, it's all combined here except for that term.